Hello and welcome to the fifth video in this series. In the last video, we derived an analogous operation to composition on affine functions. And in the previous two videos before that, we derived two other analogous operators on addition and the constant function that returns 0 on affine functions. So if you haven't watched any of those videos, I'd recommend going back and watching them right now. So this is the last derivation that we'll be doing for this second monoid. And in it, we're going to try and derive an analogous operation for the identity function on our representation, which is pairs of rationals. So I'll just load this up. We know that it's going to be a pair, so I've just left two holes there. We don't know what the definition for ID is going to be, but we do know that the meaning of ID should be extensionally equivalent to lambda xx, which is the identity function. And this is a monoid homomorphism property. So as before, we're going to meet in the middle. I'm going to work forwards and backwards. Now I'm just going to jump straight to doing a trick which we've seen in the other videos, which is where I define the pair AB to equal ID, which we don't have a definition for yet. What this allows us to do is move forward in this way and say that the meaning of ID is equal to the meaning of AB applied to X. And then we can say, well, we know what the meaning of AB is. It is A star X plus B. I only get this after I've applied the meaning of AB to X. So what I've done is I've simplified that. Okay, that's as far in the forward direction as we can go. So let's start going backwards. This is going to be a rather short proof. So clearly lambda xx applied to X is just X. Reload. And now we're in a situation where we've got X and we've got A star X plus B. So I think it's fairly clear that A is going to be 1 and B is going to be 0. But how do we show that in AGDA? Well, we're going to rely on some properties of rational numbers. So the first one we should look at is the fact that 0 is the right additive identity of any expression. So we want to get it in this form. And we need something to go in here. So I'll load that up. And really what we're just going to do is apply the rule plus identity right. Oops. And I'm going to refine that. And that requires an argument, which in this case is going to be X. Well, let's do what we did before and have a look at this. So I'm going to press meta dot. And then I'm going to press meta dot on this right identity thing. And here we get the definition which says for all X, X dot E is equivalent to X. So in our case, that's X, X plus 0Q is equivalent to X. So we are applying it in the forward direction, and the variable we want to apply it to is X. So that's worked. And we really only have one more thing to do, which is to multiply the X part of it by 1. as follows. And so here we're going to have to use conj. And the bit we don't want to touch is the +0q bit, right? We just want to apply whatever law we're going to apply to the white square. Okay, so I'll load that, That's automatically refined it. And now what are we going to do? We're going to say 1q star x is equal to x. Well, that sounds like a multiplicative identity, doesn't it? So we're going to say star identity, but this time it's on the left. So I'm going to refine that. And yeah, I guess we're going to apply that to x, and then we reload, the yellow goes away, and I think now we've got our answer. So by looking at this a star x plus b and looking at this 1 star x plus 0, we can say that 1q is the first element and 0q is the second element of this pair. And we can finally remove this here and see if the proof goes through. And there you go. We have derived the analogous ID for this particular monoid. Now that concludes the derivations, and it does actually conclude what I originally envisaged as the full set of videos I was going to make. However, I've decided I'm going to make 2 more, so I'll see you in the next one.